Hello and welcome everyone to lecture 12 of EC 3030. So in this lecture we will be introducing the concept of PN junctions. So in this class we have said that the MOSFETs are the basis of digital electronics, microprocessors and everything that we see in the electronics domain. Well, PN junctions are even more glorious. It's because PN junctions are the basis for most of the semiconductor devices, including the MOSFETs. So with that, let's get started. Today's lecture and the next couple of lectures we will be focusing mostly on chapter 6 and chapter 5, and these are the sections that will be important for today's lecture. So let's get started with looking at the MOSFET structure. So this is the MOSFET structure that we have looked into in the previous classes, where we have the gate here, oxide here, and these are the source and the drain. Now this is an N-type MOSFET, and in an N-type MOSFET the substrate or the body is P-type. Alright, so one thing that we have not talked really about in the previous lectures is that you see that the source and drain are actually oppositely doped compared to that of the substrate body. So the substrate or the body is P-type, the source and drain are N-type. Now the question that we are going to ask is that, okay, so if we have the source and drain rather than P-type, if we have the source and drain to be P-type rather than N-type, then whether this structure will work as a switch. So to understand that, let's look at the MOSFET structure here. So here we have a gate voltage applied, and then we have also a drain voltage. Now say the gate voltage is 0. Now as we have seen, if we increase the voltage, it will create a depletion region, and as we increase the voltage even further, the depletion will keep on increasing until threshold voltage, and at threshold voltage you will have the opposite carriers here. So this is P-type, so the majority carrier is whole, but when you reach the threshold voltage at the interface between the oxide and the semiconductor, you will have electrons pile up here at the interface. All right, and these electrons will participate in the conduction process. So here, because we have a drain voltage applied, these electrons will flow through the channel, giving you a current through between the drain and the source. So there will be current flowing in this external circuit. Now we had this drain voltage applied even when the gate voltage was smaller than threshold voltage, but when the voltage was smaller than threshold voltage, this did not create any current, simply because there were not these electrons here at this interface. Now the question is that, okay, so this is a P-type semiconductor. Now in the depletion region we have seen that there is no holes here, but there are a lot of holes in the body in this region where there is no depletion. Now the question is that why does current not flow from the N side to from the drain through the body to the source, where the current is carried by the holes? So that is the question, and the answer is that there is two PN junctions here. You have the body and the drain here, so there is one PN junction here and there is another PN junction here, and a PN junction is a rectifying device. It's a nonlinear device, and what happens in a PN junction is that it conducts current only in one direction, meaning that if you look at the current voltage characteristics of a PN junction, you see that when the P side is at a higher voltage than the N side, only then you will get a current here. But if the N side is at a larger voltage than the P side, there will not be any current. When the voltage on the P side is larger than the N side, that's what we call the forward bias. And in the forward bias, there can be a current flowing through the PN junction, but in the reverse bias, where the N side is at a higher voltage than the P side, there won't be any current that will be flowing through. So again, PN junction is a rectifying device which allows for current conduction only in one direction, and this is the symbol that we usually use for a PN junction or a diode. Okay. So where does PN junctions fit into the picture that we showed earlier in the class? So we have three types of materials: metal, dielectric and semiconductors. So a PN junction, you use both n-type and p-type semiconductor to create a PN junction here. So this is the PN junction, and this is one of the devices that we're studying in this class. Okay, so now the question is that why does the holes not conduct a current? And the answer is very simple, because here you see that you have a p-type region here and n-type region here. So you have a PN junction here and then another PN junction here. Alright, so now if you have a positive voltage here, which is the drain voltage, this PN junction is reverse biased, meaning that this PN junction can conduct current only in this direction, meaning that in this direction. But since N region here is higher, the higher bias voltage than this P region, there won't be a current that will be flowing through the junction here. So the only current that can flow is in this region, and the reason that the current can flow from here to here is because there are a lot of electrons here. So this region is essentially like an n-type region. So when you're talking about the current flowing through the inversion region, that's not a PN junction, that is a region. It looks like current is flowing from N region to the inverted N region to the N region in the source. On the other hand, here you have the N region through the region that is not depleted. There is an N region here and P region here, so you have a diode here, so it blocks the current from flowing through the bulk of the device. Now this region is forward biased because this is at a higher voltage, this body is higher voltage than this region, so current can actually flow through this region. But the thing is that because you have two diodes connected back to back, so if you look at this path here, this region looks like two diodes connected back to back. So although this can conduct current, this is reverse. So although if you have a drain voltage here, so this is the drain, this is the source, and this is the body. This region is, this drain to body is reverse bias. As a result, this blocks the current. Although this is forward bias, this is reverse bias, and this blocks the current. So as a result, current do not flow through the body of the semiconductor in a MOSFET, just that the current flows through the inversion region. And this essentially explains why this structure works as a MOSFET, whereas this structure won't work as a MOSFET, because in this structure current can flow irrespective of what happens at the inversion region, because there is a P region here, the drain is P type. So as soon as you apply a voltage here, the current will flow from the P on the drain side to the P in the semiconductor through the P in the source. Now you can of course invert the channel here, but the majority of the current will flow through the body to the P, because there is no PN junction at these regions, the drain to body and the source to body, there is no PN junction. So irrespective of what happens at this interface, you will always get a current. On the other hand, in a MOSFET where you have opposite doping for the source and drain, this PN junction here at the source and body and the drain and the body, those PN junctions block the current. So only current that can flow in a MOSFET is through the inversion region here, or the channel that you form by applying a voltage larger than the threshold voltage at this interface. All right.